All right, let's tell me about colligative properties. What does that term reference?
The properties when you put solute into solvent? Or the
Solute into what?
solvent.
Solvent. Okay. So,
Changes in the properties of a liquid with a solute.
so I'm going to change the liquid, or sorry, I'm going to change the pure solutions, the pure substance's properties by adding a solute to it. You can't say liquid though. Why?
Because not all solutions are liquid.
Yeah, it could be. It's almost always a liquid, but it could be a solid. It could be an alloy. How does it change the liquid state of the substance?
Lowers the freezing
Okay.
point.
Lowers the freezing point, raises the boiling point, basically increases the range. Of the liquid state. It's liquid longer. All right, so what happens when a salt is added to water? So when you're boiling something, why is it boiling?
Added energy.
You have substance has enough kinetic energy to do what? But it's got to do something to change from a liquid to a gas. What's it got to do? What? Yeah, you can't use the word in the answer. What is actually occurring when that happens, when it boils? Okay, why is the question?
Is it breaking the?
Yeah. So it's boiling because it has enough kinetic energy to overcome the intermolecular forces. So that's just boiling. So what happens when I add this solute? No.
Takes some more energy.
The intermolecular forces are now stronger than they were before. So you need a higher amount of kinetic energy for the water molecule to break free, because now the water molecule is not just breaking free of itself, it's breaking free of the solute. So when it was just a pure substance, it was a water molecule trying to break free from another water molecule. Now it's a water molecule trying to break free of, say, a sodium ion. And so this H has a partial positive charge, where this sodium has a full-fledged plus charge. So the amount of energy needed to get those to let go of each other is increased because the attractive force between the two is greater. All right, what about why does that freezing point go down?
Is it the same reason?
Okay.
The opposite, like you can't create the crystal minus because the sodium is in there in the lake.
Okay, that's pretty much it. So basically for the same reasons. And by that, we mean that the intermolecular forces for the sodium ion are going to be, to the water molecule, are going to be stronger than the water to the water. So it rearranges the crystal matrix structure. So the So your solid state is only there because the molecules or the ions or the atoms are a nice organized structure, like a bunch of Legos linked together. And what we're doing here is taking some of the Legos out and putting in Lincoln logs or rocks. It is not organized anymore, so they can't stick to each other, so the whole solid structure falls apart, and now it's less organized, so it's in a liquid state. Did you have fun with this one? Not really? It's actually a lot easier when you think about what's going on. The answer, you need to have what units?
Moles per liter?
Moles per liter, that's it. You just need the total number of moles and the total number of liters. So the total number of liters one's pretty easy to get, right? You just add the total volumes up. So I've got 250, 400, and 2. So that's the total. I'll put 0.4 and 0.25 here. So I already got half of it. I've got my 2.65 liters. So I need to have that in the denominator, and I need a number of moles in the numerator. So how many moles do I have in my first substance? Well, it's 1.3 moles per liter NaCl, and I've got 0.25 liters. So the liters cancel out, and I've got moles NaCl. And then my next calculation is 1.75 moles per liter, NaCl per liter divided by 0.4 liters, and the liters cancels out, and I got moles NaCl. So I've got 1.75 times 0.4. So it's 0.7 moles, and then I got 1.3 times 0.25, and I got 0.325. So I'm just going to add those guys together, and I've got a total of 1.025 moles. I'm going to divide that by my 2.65 liters, and I get 0.39 moles per liter. That good? Is it? Sure, yeah. 1 sig fig in that 400 milliliters. I guess I should have put a decimal place there or something. But not too hard, right? Do we want to talk about where you're having hiccups with this?
I initially thought that you would find like the individual, like you would do the like 1.3, you'd find like the individual concentration of both for some reason. You know what I mean?
Because that is the concentration, that 1.3.
But I know what you mean, because that's what I started to do too.
Yeah.
I eventually figured it out,
Yeah.
but it took a long time.
So-
I think I was trying to like find averages and
Oh.
stuff like that.
Okay.
So like I took the 1.3 moles, divided it by the 0.25 liters.
Wait,
and got
divided
the
it?
answer. Yeah, because isn't the,
No, because that would give you moles per liter squared.
okay. That was my initial thought. but-
Okay. Which one of these two compounds is a better electrolyte? Okay. I mean, these are both electrolytes. These things are both in Gatorade, but one's just a little bit better. And what was the reasoning? Yeah, because this has 3 parts and this has 2 parts. Even though the overall charges are the same, what's a good analogy with this? They're both soluble, so for the most practical reason, no.
Even if one's higher on solubility rules?
Yeah, they're both soluble. It's not, I mean, it barely matters. You're not going to put so much of these things into Gatorade or something else that would want them to be used as an electrolyte to cause some of it to be insoluble and sitting at the bottom. That's not going to be an issue. Really what we've got here is one breaks up into 3 pieces and one breaks up into 2 pieces.
So there are 3 pieces to conduct electricity instead of 2.
Correct. There really isn't anything else to it. There's 3 things that can do work versus 2 things that can do work. So, and then you can think about the other things that this can do, right? So if I throw 3 things into my solid, my snow, the calcium chloride is going to be able to disrupt more in more places because it's got 3 things to be doing the disrupting. Or if we're talking about the boiling of the water molecule is now trying to get away from 3 different particles as opposed to just 2 different particles.
So just to be clear, the 3 parts are 2 chlorides, 1
Yep,
calcium.
absolutely, yeah. For this one, I'm gonna get a Ca with a +2 charge, and I'm gonna get a Cl negative and a Cl negative, and over here I'm gonna get an Mg with a +2 charge and an SO4 with a -2 charge. I just wanted to make sure that we didn't try to break this sulfate up into more pieces, because it's not going to. It is a polyatomic ion and it is stable. So I'm glad nobody said like, what would that be, 6 pieces for the magnesium sulfate, because that's not gonna happen. Okay, so percent solution for this calcium chloride, create a 400 milli, okay, so 35 grams divided by 400 milliliters times 100. So what do we get here? So 9% mass to volume?
Why is it 9, not 8.8?
There's only one sig fig right there on the 400.
The mass, volume, so we need to specify that.
Yeah. If it's not specified, you don't know what they used, and it almost never matters, but sometimes does. Okay, so we've got this beer and this alcohol, and I got 3.5%. So 3.5 is my percent answer. This is 100 times, and it's a 454 milliliters. So I don't know that thing right there. So my X is going to be equal to 3.5 times 454 divided by 100. And so 3.5 times 454 divided by 100. I get 15.89%, so about 16, no, not percent, milliliters. So about 16 milliliters. So this 454 milliliter beer, only 16 milliliters of it are actually ethanol. Does anybody know what beer that is? No, Coors Light's pretty high. It's like almost 6. Same thing with Budweiser. It's,
Something European.
yep.
Stella?
Most sold beer in the world. Oh, no. Guinness. Super low alcohol content as to regular beer. Most beer.
What's most beer? What's the alcohol content of most beer?
Of most beer, I guess if we want to say most beer, I would, so with the regular commercial beers, it's going to be 5.5 to just under 6, which would be all like the Millers and the Budweisers and the Coors. But around here,
Probably like 8, more like 8.
8, 7, 9. The craft brews are always going to be more because they're always trying to make it taste different. Yeah. That's usually not the actual problem, like headache wise the next day. There's just, did they filter everything out that's a toxin or not? And there are certain places around here that don't filter and does bad things to your body. Mostly Double Mountain. So which equations did we use for the for these guys? We used mass to volume and volume to volume. All right, so what's the Fahrenheit freezing temperature of 2.5 magnesium chloride solution? All right, so our equation is the change in the temperature of the freezing is equal to the N times the Kf times the molarity. And so I've got, this is magnesium chloride, so what's my N value going to be? 3. Mg plus 2, so Cl, I'm going to need 2 of those to go along with that. So then my N value is going to be 3. And then my Kf was given at 1.86 degrees C molar. And then I was told that I've got a 2.5 molar solution. So my molar count cancels out. So I get I get 13.5 degrees Celsius. All right, so that part's pretty simple. This next part can be confusing. So what did we just calculate? We calculated the change in the freezing point of Celsius, right? So what temperature is the water now freezing at? Negative 13.5. Okay, great. So I've got negative 13.5. Now you take that negative 13.5 number and you throw it into the equation and convert over to Fahrenheit. So this, the new freezing is negative 13.5 degrees C. And now I need to convert that over. And so it's temperature Fahrenheit is equal to
Degrees Celsius times 9 fifths or something.
I needed to go up and then I need to add 32 to it. Alright, so times 9 divided by 5 equals plus 32 equals, yep, that looks good. Does that value make sense? 7.7 degrees Fahrenheit? Right? I'm under 0 degrees Celsius and I'm under 32 degrees Fahrenheit. So those seems to make sense.
So when you're doing this and you're doing the N value is only the parts of the solute, is that right? Like you wouldn't count
Correct.
the water?
Oh, absolutely not.
Okay.
No, no. The water is the thing that you're being acted on. So
Okay.
the N value is just the number of pieces that is going to break up into or not break up into. What would your number be for sugar? So let's say glucose.
Is that C6?
C6H12O6. 1. It doesn't break up in anything at all. It stays itself as a glucose molecule. So it's in your bloodstream, it's a glucose molecule, right? So if you dropped it into snow, would it disassociate? It didn't disassociate in my bloodstream, so it's not going to disassociate on my porch that's covered in snow.